Outer space looks black, but the entire universe used to be this color. How's that possible? Let's find out. Stars and galaxies notwithstanding, space is pitch black. So pick a dark spot in the sky and point an analog satellite dish at it. You might expect to get nothing, but you don't. You get static. Pick another point and more static. Move your dish yet again, static. Even accounting for all possible types of interference, no matter how you orient your dish, there's this constant underlying microwave band static that's just always there in the darkness of space, emitting the same pattern over and over. Now, since we pick up this mysterious static from every direction we look, it would seem to be coming from a source that exists literally everywhere on the sky. Problem is, we don't know of any source anywhere that would emit this observed pattern of microwave emission, so where's it coming from? Aliens. No, it's not aliens. It's never aliens. But what if I told you that the source of the static, which we call the cosmic microwave background, or CMB, was the process that formed the first atoms in the universe almost 13.5 billion years ago? And what if I also told you that the source of the CMB also caused all of space to look orange for millions of years? That's right, the universe used to be orange. To understand how this could be true, we first need to take a brief detour into your toaster. Turn on your toaster. The heating elements glow a pale reddish color. That glow isn't ambient light reflecting off the toaster, it's light being emitted by the toaster itself. If you were to analyze that glow with instruments less limited than human eyes, you'd realize that the toaster isn't just emitting pale red light, it's emitting electromagnetic waves of all wavelengths. Moreover, the intensity at different wavelengths is in very specific proportions that trace out a graph very close to this. That emission pattern, represented by the graph, is called the toaster's thermal spectrum, or really an idealization of a thermal spectrum called a black body spectrum. Now, everything has a temperature, so everything has a thermal spectrum and emits all electromagnetic wavelengths. You, a taco, the sun, everything. In fact, it's called a thermal spectrum because the light is generated by the random motions of particles in the material, and those random motions are themselves a reflection of temperature. Now, if you go really low in temperature, down to 2.7 degrees above absolute zero, the peak shifts way into microwave wavelengths and, lo and behold, exactly matches the CMB, and I mean exactly. The CMB is one of the closest things to a mathematically perfect thermal spectrum that has ever been observed. Problem is, space is pretty much empty. There's nothing really in there to have a temperature, much less the very specific temperature of 2.7 Kelvin, so why does the CMB look like a thermal spectrum at all? To answer that, and to see why space used to be orange, we need to turn the clock back to about 400,000 years after the Big Bang, give or take. During that era, a soup of charged particles with a temperature of several thousand degrees permeated all of space. At this temperature, it's too hot for electrons and protons to even coalesce into atoms, let alone stars, planets, or galaxies. This ionized soup is called a plasma, and just like toasters, people, and tacos, it was emitting a thermal distribution of electromagnetic waves. But because there were no neutral atoms yet, the light the plasma emitted just couldn't travel very far before it would run into an electron and ricochet, like in a pinball game. So if you took the TARDIS back to this era and could somehow keep it from melting, you wouldn't be able to see very far on the view screen. Maybe a few thousand light years, which sounds like a lot, but is basically zero visibility in astronomical terms. So at this moment, it was as if flashbulbs were constantly going off everywhere in space, but the light was being snuffed out by a fog. Now, as this plasma cooled, its temperature eventually dropped below the 3,000 or so degree mark, where neutral atoms could finally form. With no more free electrons to redirect the light, the universe became, for the very first time, transparent. The light that the plasma had emitted then, just before it neutralized, was like one last hurrah, one final flash of an infinite number of orange bulbs going off at every point in the universe, more or less simultaneously. And now, that light could free stream through the universe forever. Before, during, and after this event, space was expanding. That's what thinned out the plasma and made it cool down in the first place. But as we talked about in a prior episode that you can revisit here, expanding space stretches the wavelength of free streaming light through a process called cosmological redshift. So, over the course of a few million years, that orangey thermal spectrum of light was redshifted to longer and longer wavelengths, becoming toaster red and eventually infrared, so that to human eyes, the sky eventually turned dark. If you throw in another 13 plus billion years of space expansion, All that light has redshifted into the microwave band to become what we today perceive as the CMB. And all those atoms from that plasma, well, they managed to clump, become stars, galaxies, and through a complicated process of cosmic recycling, us. So the CMB, or more specifically the shape of its thermal spectrum, is pretty compelling evidence that when it comes to the color of space, black is the new orange. Now the CMB is interesting for a lot of other reasons besides its thermal character, so I'm sure you guys will have questions about it. I'll tackle as many as I can on the next episode of Space Time. Last week, I challenged you to stabilize a gyro-driven Star Fox barrel roll. A lot of you emailed in responses, and a lot of you got it right. The first 5 of you who emailed correct answers, and I apologize in advance if I mispronounce your names, were Marcus Kesselring, Cameron Moran, Matthias Ola, Thomas Sue, and Jacob Stuck. Good work. The rest of your names will be scrolling below as I explain the answer we were looking for. The trick was to cancel out all the intermediate angular momentum vectors produced as the flywheel with forward-pointing angular momentum rotates to end up with backward-pointing angular momentum. And the solution is to have 2 flywheels, both with forward-pointing angular momentum, that you rotate into the reverse orientation in opposite senses. That way, any sideways intermediate angular momentum that gets produced is canceled out. The short YouTube video here shows a demo of this principle in action. An answer that some of you submitted, that technically isn't wrong but wasn't what we were going for, is to take the already spinning flywheel, just one of them, and slow down its spin. In response, the ship would have to be torqued the other way. And technically that works, but you don't get nearly as much torque amplification or leverage as you do from actually rotating a gyroscope without changing its spin. A few of you asked, wouldn't the extra mass of the gyroscopes weigh just as much as extra mass from fuel? Answer, not necessarily. If some fictitious, really light but really strong material could be spun sufficiently fast, you could store up a lot of angular momentum with very little mass. And to everyone who pointed out that we got the aileron flap directions wrong in the video, noted, annotation added, and thanks for keeping us accurate.
The universe is expanding. If you zoom out far enough, you'll find that everywhere in the universe is moving away from everywhere else. But once you know the universe is expanding, you might wonder if it's going to keep expanding somehow, or eventually stop and crunch in on itself because of the attractive force of gravity. Well, all you have to do is point your telescope at a distant galaxy, measure how fast it's moving away from us, wait about 1 million years, and then do the same thing again to see if the galaxy is moving faster or slower than before. But if you don't have 1 million years to spare, here's what you do. You look at different galaxies. Because light takes time to reach us, when we look at a galaxy far, far away, we see it as it was a long time ago. So looking at a bunch of galaxies different distances away is kind of a rough proxy for looking at the same galaxy at different times. The light from the stars in a distant galaxy can tell us 2 basic things. First, its speed. Light from anything moving away from you becomes redder in color, kind of like how police sirens get lower in pitch when moving away. This red shifting of light tells us exactly how fast stars are moving away from us. If the light from a star is 5% redder than it should be, it means the star is moving away from us at 5% the speed of light. Light can also tell us how far away a star and its parent galaxy are. When you're driving at night, you can tell how far away a motorcycle is by comparing how bright its headlight seems to you to how bright it would be if you were right in front of it. The same trick works with stars. There's a rare kind of supernova explosion that's like a standard interstellar headlight. It's about 5 billion times brighter than our sun, and crucially, it's very consistent in its brightness. These supernovas only happen a few times in a galaxy every 1,000 years, but there are enough galaxies in the universe that if you look closely at a wide enough patch of sky, it's possible to see a dozen of them go off in a month. By comparing the brightness as seen here on Earth with how bright we know each of them should be, we can work out how far away each supernova is. The dimmer its light, the farther away it is. So the color of a Type 1a supernova tells us how fast it's moving away from us, and its brightness is like a ruler, telling us how far away it is, or because light takes time to get here, how long ago we're measuring its speed. By measuring the speeds of different supernovas at different distances, aka different times in the past, we can plot the expansion of the universe over time. A straight line means the universe is expanding at a constant rate. A curve means it's speeding up or slowing down. For a long time, we thought the line was straight, or slightly curved in the slowing down direction. But when astronomers finally looked carefully at supernovas in super distant galaxies, they discovered to their surprise that the universe is expanding faster now than it was long ago. The universe's expansion is accelerating. P.S. We have a few basic ideas for why the universe is accelerating, but we still don't really know why it's happening. One of the simplest and most popular ideas is that there's an everywhere permeating vacuum energy with negative pressure, which we've never detected in any way other than by measuring the acceleration of the universe. So we call it dark energy. Thanks to the Wide Field Infrared Survey Telescope project at NASA Goddard Space Flight Center and the Space Telescope Science Institute for supporting this video. WFIRST is planned to launch in the mid-2020s and will, among other things, allow us to see a much wider swath of the sky at Hubble-like resolutions and even farther distances, and thus hunt for more supernovas many billions of light years away. That'll help us understand whether the acceleration of the universe is different in different parts of the universe or whether it's changed over time, which should help us figure out what exactly dark energy is.